Okay, a couple of review problems. The second one that I'm going to do with you is really going to help you with the final product that we have to do for this unit, the Where in the World is Carmen Sandiego. So you're also going to need to know how to do some of these earthquake and decimal problems as well. So a couple of review problems. Remember the review that goes with this unit, I only want you to do evens or odds. So don't do all of those. That would take you a long time. Okay, so for this one, we did these the last couple days. So earthquake 1 is 85,000 times more intense than earthquake 2, which is 4.1 on the Richter scale. What is the rating of earthquake number 1? Okay, so quake number 1 is the most intense one. So if I take the weaker one, which is earthquake 2, multiply it by 85,000, I should get the intensity of earthquake number 1. So this is going to be our I from the formula. And this is I sub 0. Quake 1 is stronger than quake 2. So for my formula, I is equal to 85,000, or 8,500, sorry, times I sub 0, which is my weaker one. So I need to find out that difference between the two quakes by using my log formula. So I have log, remember it's I over I sub 0. So if I substitute for my numerator, I get 8,500 I sub 0 over I sub 0, which is my weaker quake. These are going to cancel. And a log of 8,500 is 3.929. And now I have to go back and apply that to my ratings. So quake number 2 is my weaker one. It's quack. So this is my weaker, plus the 3.29929 is going to give me quake number 1, which is my stronger one. So my weaker one was 4.1 plus 3.929 gives me 8.029. And that is my stronger one, quake number 1 rating. All right, so there you have that one. So then we have this one. So this one might take us just a bit of time, and you need to make sure you have that calculator with you. Okay, so thank you, Mr. Abundis, for the Real Neat Things Live Here planets. So on the planet Real Neat Things Live Here, scientists use the radioactive isotope germanium-9 to determine the date of different artifacts. So a body was discovered. This would be a good problem for forensics if you guys were in forensics. So a body is discovered that has 60% of the normal germanium-9 of a living person. After 12,000 years, it would decay to about 39.4% of its original body. So I need to know how many years ago was the germanium-9 at 90%, and how long ago was the person alive? How many years ago? Okay, so if you recall from the beginning of this unit, I drew some timelines, and a timeline is really going to help you on this one. So on my timeline, I'm going to add my percent of the body remaining. So I'm going to use that as P. So remember, bodies are going to decay over a certain time period. Okay, so here's my timeline, and I'm going to put on there what I know. So the first thing I know is that right now, at this point today, the body was discovered that had 60% of the germanium-9 of a living person. So I'm going to do this as now, T equals 0. If I use P as my percent of the germanium-9 of the body remaining, this is going to be 0.6 P for 60%. It's not really the body, it's the isotope. Okay, so then it gives me the information that after 12,000 years, so after 12,000 years have passed, that isotope is going to decay to 39.42%. So as I move forward on my timeline, T is equal to 12,000. And at that time, I've got 0.3942 of the isotope remaining, or 39.42%. Okay, so it wants to know, number one, how many years ago was the isotope at 90%? So that's going to go backwards on my timeline. So this one I don't know T. But I do know that I want to know I have 90% remaining. And then for problem number 2, we're going to go backwards in time a little bit more. And we're going to figure out 100%. 100% or 1 times the isotope. Okay, so the first thing I have to do is find my decay rate. So to find my decay rate, I have to use this information right here. So I'm back to exponentials. So find the decay rate. So my latter one, remember it's decaying, so I want to do my 12,000 year one because it's a smaller one, and I want to go back in time. So I'm going to set this equal to my 39.42 P. And remember, I'm using exponential growth and decay now. And I'm doing continuous growth and decay. So I'm doing the A equals P e to the RT that we've used before. Okay, so my current is now 0.6 P. E. I don't know my rate. I'm going to call it K. And remember, that's times 12,000. So if you set it up the other way and went from the 0.6 to the 39.42, you're going to get a positive decay rate. So you just have to realize how you're setting your problems up. Okay, so if I divide both sides here, I can see that my P's are going to cancel. So my ratio is simply 0.3492, 3942 over 0.6 equals E to the 12,000 K. Now I can change to a logarithm, natural log. 0.3942 over 0.6. And if you can see ahead a little bit, you're going to have to divide that by 12,000 like we did before. And I get a decay rate about negative 0.00004035. Okay, so I want to use that value for the rest of my problem. I don't want to change that to a percent because then I'm just going to have to change it back. Okay, so for number one was where I wanted to figure out the 0.9 P. Okay, so remember, if I go from 0.9 to 0.6, it's decaying. So my K is negative. So I'm going to go in that direction because it makes more sense. So I'm going to go 0.9p for my percent remaining equals 0.6p E. My K is equal to negative 0.000035. And I don't know the time, so T. So my P's are going to cancel again. So I get 0.9 over 0.6 equals E to that exponent. I can tell you when you're doing the project, be very careful that you have the right number of zeros, because if you don't, it's going to mess everything up. Okay, so now I can change to my logarithm. I know I'm going to have to divide by that decimal. And if you put that in your calculator correctly, you get 11,585 years ago. And that would be at 90%. This is very similar to what your project is going to be, except you have to do a lot of problem solving along the way. Okay, so for number 2, now I want to do basically the same thing, but I want to find out how long ago there was 100% of that isotope remaining, so when the body was in full tact. Okay, so you've got to make a choice, like which value do you want to go from? So I choose to go from the now time because it just makes sense to me. And I'm going to go figure out how long ago it was in full tact. So I'm going to set my equation equal to the 1p. I'm going to use my ratio that it is now at 0.6p. Basically, everything else is the same. Okay, so my p's cancel. I can kind of see ahead what's going to happen. I'm going to have 1 over 0.6. I'm going to have to take the natural log of that. And I'm going to have to divide by the ratio, or the decimal. So if you put that in your calculator, P is about 14,595 years ago. Where the isotope was at 100%. Okay, so as a lead into the project, or the final activity, I guess, the Where in the World is Carmen Sandiego? You're going to have to show me all your work. It's going to have to be legible, and it's going to have to be logical, because that's going to be what most of the grading is based on, as well as your final conclusion. Like, do you actually find where in the world she is? So there you go. Remember, if you start working on the review, only do evens or odds.